Just right here. I'll do this. I remember. I'll be back in a second. You know, we need to go, and we don't need to. This thing of being, you know, very. And it's. But like, they count it as still. Oh. That's it. Yes, you should be. That's. Really? Oh, man.
Probably, honestly, not until maybe like 7 or 8, like after this. But yeah, there's a lot of groundwork we need to get first.
Is there an advanced MATLAB class?
Nothing that's just straight MATLAB. It's everything's like applied. I would say.
Is there, what, do we use Simulink at all?
We used to have a similar class. No one's taught it in a while. Yeah, I haven't seen it.
I know,
It was, I honestly don't know. The last time it was taught was actually before I started here.
Okay.
So, but my impression was that they had a lot of.
You actually get behind there.
Yeah, I think she's interested. That might be something.
I think played around with it. You could just add it and then just doing it.
So last week. Yeah. We're all, yeah, haven't given it out, so. I don't even know what it does. It's not, yeah. Like I'm not. Yeah. Yeah. Well, are we gonna be implementing this stuff second about
Probably like 7 or 8. There's it's gonna be a while because there's a lot of groundwork.
Honestly, on the engine, I'm taking individual. Yeah, no. I would be so hot.
A little,
So many,
it's really hot.
only 104 now.
Stand back. Retabling the whole time. Retabling the whole market car festival. Huh?
I was having to deal with you. Maybe have single players showing from the 40s or something.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good, keeping cool, hopefully. It's really hot outside, so make sure you guys stay cool. I think it cools down over the weekend, but stay inside if you can. Stay hydrated and do everything you can. Stay out of the heat. Okay. All right, so the plan for today is we're starting a new set of lecture notes, and so we're starting with what I call kind of the classical methods. So these are methods that kind of like the old school way of doing optimization. I think that's probably the best way to describe it. There will be concepts that you guys have seen before. It might have been kind of a passing thing that you covered through calculus class, but today, we'll really kind of dive into it. And this will kind of form kind of the foundation for everything that we do for the rest of the class. So, right. Any questions I can answer before we get started today? Okay. All right. So let's go ahead and get started. All right. So today we're going to start with just kind of the easiest kind of method that you can do, which is I call the unconstrained classical optimization. Okay. So this first part of the class, we're going to be covering what I call kind of the classical methods. And the reason they're called classical methods is that these are methods that you can do, without a computer. In fact, another name for these are calculus-based methods. Okay. Because before the age of like computers and programming and all that stuff, mathematicians have been interested in finding optimal values for functions for forever. And so this is kind of their old way of doing it. And if I have to be kind of perfectly honest, in the world of kind of, I would say modern optimization today, pretty much nobody uses the classical methods anymore. These are mostly obsolete. We have more advanced algorithms now. We make use of computer code. So you're not really going to be using these in any kind of serious way or for any kind of serious problem. But just like anything, you're learning for the first time. You kind of have to start with the basics. And so, that's kind of why we do this, is to kind of build a foundation, get some intuition, because even though, these exact methods we're not going to be using in the future, the intuition that you build and kind of the background knowledge is going to be important for understanding the more advanced algorithms. And so, like I just mentioned, the classical methods are what's known as calculus-based methods, or to be more specific, derivative-based methods. And just like that name implies, taking the derivative of our objective function is going to be kind of the main thing that we're going to be doing. All right, so for today, we're gonna be focusing on single variable problems. So we're looking at one D optimization. You've probably already done these before in your previous calculus class, but it's kind of good to review. And then what we'll do on Tuesdays, we'll apply these same methods to multivariable situations. All right, any questions on this before we move on? Okay, so let's look at single variable optimization. Okay, so a single variable optimization kind of represents kind of the absolute simplest case or absolute simplest kind of optimization that you can do. Okay, and so it's a problem with just a single design variable, and you want to find its optimal value. Okay. And we'll take it even a step further today and say that this will be a case without any constraints at all. Okay, so the only thing we have is just one design variable and one objective function. And so, of course, the goal is to find the value of the design variable that either maximizes or minimizes the objective function. Okay. For the most part, we're going to be doing minimization problems in this class, but just know that, to turn a minimization problem into a maximization problem is really easy. You just take the negative of it. That's kind of how we would we would describe the problem using kind of optimization jargon or optimizations. But this is a problem that you've seen before in calculus, and so probably the terminology that you've used there is you want to find either the maxima, the minima, or the extrema of the function. All right, so let's draw it out. So the nice thing about one-dimensional problems is that we can very easily sketch it out and we can kind of visualize things much more easily. Okay, so for today, I'm gonna be using kind of, calculus based variables, so you'll see me use x a lot, you'll see me use f of x. So x here is our design variable. So the values on the horizontal axis will represent different values of that design variable. And then the vertical axis will represent our objective function, or the value of our objective. Okay. So let's say that we have an objective function that that kind of follows the path, this path. So let's say that we have something that looks like this. Okay, so what do we see when we look at this function here? So, anytime we have a maxima or minima is basically anytime that there's a peak or a valley in the function, right? You can say that this is a maxima, this right here is a maxima. Whereas all the valleys, or the parts where the function kind of reaches the minima, those are the minimum. Okay. So, you'll notice here that I labeled every time that the function peaks locally, we call that a maxima. But of course, there's one maxima here that's greater than all the others, and one minima that's more negative or less than all the others too, right? And so, we have to kind of make the distinction between a local extrema versus a global extreme. So a local extrema so extrema is kind of the generic term I use to refer to either max or min. Okay. A local extrema is basically, either the highest point or the lowest point in its relative neighborhood. Question in the chat. Question, is an extrema a maxima? So yes, so extrema can refer to either a maxima or a minimum. Yeah, it's kind of the generic term for both. Yeah, so we have a local extrema if everything around it and its kind of immediate neighborhood is either less than. So if everything in the immediate neighborhood is less than that, it is a maxima. And if everything is greater than that point, then it is a local minimum. Okay. There's a more precise kind of mathematical definition which uses variables, but I think visually, we can all kind of see local extreme. Okay. And so we can contrast that with a global extrema. So global extrema is one such that all if you account for all values of the function for all values of x, there's no other point where it's either greater than or less than that point. So if all other points are less than or greater than, then we have a global extreme. All right, so these definitions, I think they're pretty straightforward, but you'll be surprised that a lot of optimization algorithms actually struggle to differentiate between local and global extreme, and that's going to be true for the classical methods that we're going to go over today. That's even true for even a lot of the very sophisticated methods that we'll see later on as well, right? It's something that is a big struggle for all optimization algorithms is to typically what optimization algorithms are good to do, they're good to finding the closest extrema to it. But if you want to look beyond that, it can be kind of a struggle. But so that's why it's kind of important to kind of make this distinction. Yeah. Okay. Any questions on this so far? Okay. So how do we find the extrema in a function like this? Let me go back up to the picture here. Okay. What is something that you notice about the function at all of the extrema? So not only the maxima, but the minima as well. Okay. So one thing that you should notice is that if you draw the slope of the curve at those points, it's going to be 0, right? So if you draw kind of a tangent line, this maxima here, you can see that it's a flat line. The tangent line at the minima is also a flat line. The maxima also is a flat line. And this one down here is also a flat line as well. Okay. And so how do we typically find the slope of a function that we have? Well, we take its derivative. And so that's basically the condition, and that's kind of the crux of all classical optimization, that if you take the derivative of the function and it's equal to 0 at that point, then you have an extrema at that point. And so basically the way to kind of formulate this in a mathematical form is that if df dx is equal to 0 at x is equal to x star, where x star is the the value of the or that's the extreme value. Okay. Then x is equal to x star is a local extrema of the function. And so that simple statement there kind of tells us, exactly what we need to do for classical optimization. So the first step in every classical optimization is to take your objective function, take its derivative, and set it equal to 0. You can set it equal to 0, and then what we'll do from there is solve for the value of x that satisfies that equation. I'm gonna box that right there, because that's the most important step. That's what we're gonna be doing a lot of over the next couple of weeks. Okay. So, I mentioned today that, you've probably done this before, you've probably done this in your calculus class before, so just kind of doing it into. Any questions on this so far? Okay. All right, so that's the first step. So we're gonna take the derivative of our objective function, set it equal to 0, solve for x, right? Pretty straightforward. But if you kind of read the definition of this part here, this is only really good enough for us to solve for the extreme. And so it doesn't really tell us any information about whether it's a maxima or a minima, or if it's a global max or a global min. Okay. So the next step is to determine, whether this point that we're solving for here is either a maxima or a minima, or neither. Because usually in an optimization problem, we're interested in just one or the other. So we're interested in, either the minimization of the function or the maximization of the problem. So, if we find an extrema using the derivative method, we need to know whether we're a max or a min. Okay, especially for functions that are going to have multiple extremes, which is pretty common for this part. Okay. So that's going to be the second part of the classical methods. Okay, so we need to check. So for every location, where the derivative is 0 for f of x, what we need to do is we need to take higher order derivatives in order to classify that extreme. So we're going to take higher order derivatives, and then depending on the sign of those higher order derivatives, that's going to tell us, what kind of max or min is. So there's quite a few different scenarios that you can have here, because in the best case scenario, you take another derivative, which is the second derivative, you get a positive or negative number that tells you something. But sometimes you have to keep going. Sometimes you have to actually keep taking derivatives to find the answer. So let's go over each case. Okay. So these are going to be a little bit confusing the way that they're kind of stated, but there's kind of a reason. All right. So if the value of the next highest derivative evaluated at the extrema If this value is greater than 0. And the order of the current derivative is even. So if both those conditions are true, so if we take the second, so for instance, if we take the second order derivative has an even order. And if that value is greater than 0, then what we have is a minimum. All right, so that's kind of the best case scenario, or one of the best case scenarios. Okay. All right, second case, if the value of the next highest derivative if the value of the next highest derivative evaluated at the extrema is less than 0, and if the order of this derivative is even, and so in this case, if both of those conditions are true, then what we have is a maximum. You've probably seen these conditions before in calculus, I think probably in calculus, they describe the function either concave or convex, concave up, concave down. I don't exactly remember the exact, but something similar to that, you guys probably heard, right? You probably haven't heard the addendum to this, which is, you have to make sure that the derivative order is even. And there's a reason for that, because, one possibility that you may have is that if you take a second derivative of the function and you plug in the extrema, you might still get 0, depending on the function. Okay. If the value of the next highest derivative evaluated at the extrema is 0, and so if it's 0, then we can't tell whether it's a max or a min. So at that point, you have to take another derivative. And so basically, you're going to keep taking derivatives and evaluating at the extrema until you get a non-zero number. Okay. And so you're going to take another derivative and then just kind of restart this algorithm kind of from the top. All right, so we have one more case to go. This sounds very complicated just because it's, you know, there's just kind of 4 different cases here, but once you actually try it out in practice, it's actually pretty straightforward. But the last case here is that if the value of the next highest order derivative evaluated at the extrema is non-zero and the order of the derivative is odd, then you have a neither a max or a min, you have a saddle point. So if you're curious what a saddle point looks like, it's kind of a point where a function comes up and kind of flattens out for just a second and then continues back up. So this point right here, right in the middle, you know, technically the slope there is 0, and so you're gonna solve for that point when you take the first derivative. But you can see from here that it's neither a maximum or a minimum. It's not even an extreme because everything in the neighborhood is kind of right in the middle. You want to be careful of those points because those points those points are never going to be the answer to an optimization problem. All right, any questions on this? Okay, let's do an example. So that was kind of a lot of jargon, a lot of words. Honestly, maybe a little bit too many words to describe something that's quite simple. So let's do an example just so that you can see the options. Okay, so let's consider this 1D optimization problem. So let's consider this objective function. Our objective function will be f of x equal to x squared minus 8x plus 16. Okay. All right, so fairly straightforward quadratic equation. And so what we want to do is we want to find the optimal value for this function here. Okay. And we want to find if it's either a maxima, a minimum, or neither. So, okay. So we have our function here. It's fairly straightforward. So let's do our first step in classical optimization. So let's take the derivative of this. We're going to take df dx. So we're just going to do simple power rule here. So we're just going to take each term and take the derivative of it. Okay. The derivative of x squared is 2x. A derivative of minus 8x is just minus 8. The last term there is a plus 16. 16 is just a constant, and so we're just going to set that the derivative of that is just going to be equal to 0. Okay. Okay. And so to find the extrema, we're going to set this whole thing equal to 0. And then we're gonna take this function here and solve for x. Okay, so I'm gonna go ahead and rewrite that. So we have 2x minus 8 is equal to 0. Let me add 8 to both sides. And so adding 8 to both sides, we have 2x is equal to 8. Okay. We're gonna divide both sides by 2. And so dividing both sides by 2 will give us our value of x. Which is equal to 4. Okay, so 4 here is the value of the extrema for this function. All right, so now that we have the value of the extrema, let's classify this, and so whether this is a max, a min, or neither. So let's take another derivative. And so the second derivative in this case is d squared f dx squared. We're going to take the derivative of 2x minus 8. And so the derivative of that is just going to be 2. Right, so you can see this is a positive number. The other thing that we notice is that you know, the derivative order in this case is even. It's 2. And so if we look back at our kind of our chart above, or kind of our flow chart that you can call it, right? So we have a second order derivative, and so we know the derivative order is even. We have a value that's greater than 0. In fact, this time we don't even have to plug in any value of x, because it's just a constant. And so that tells us that this extrema of x is equal to 4 is a minimum. And so if you plot the function, you will see kind of exactly the same thing. So if we plot it, plot of this function looks something like this. So it's just a simple parabola, and the parabola reaches the minima at x is equal to 4. All right, any questions on this example here? Okay, all right, so that's good. That's our first you know, classical optimization problem. Let's do one that's a little bit more advanced. So in this example, we're going to consider the objective function to be the following. Okay, so we have 12x to the 5th. 45x to the 4th. Plus 40x cubed plus 5. Okay. So we have a 5th order polynomial in this case. All right, so we want to do the same things as before. So in this case, since we have a fifth order polynomial, we're gonna have multiple extrema. So we're gonna have just more than one value of x, where this either repeats the max or the min. Okay, so you want to find all the extrema. And we're going to classify them as either maxima, minima, or mean. All right. So even though our function is a little bit more complicated here, we're going to follow the exact same procedure. So our first step is going to be to set this function, or take the derivative of this function, set it equal to 0. Take df dx. So same thing we did before, we're going to go term by term. Just use the power rule, just take the derivatives. Okay? And so if we do that, derivative of the first term will be 60x to the fourth. Our second term here will be 45 times 4, which is 180 x cubed plus derivative of 40x cubed, that is 120 x squared. And then of course, derivative of the constant value 5 is just 0. So that term just goes. Okay. And so we're going to set this entire expression here equal to 0. All right, so we have to do a little bit of algebra here, and so there's a bit of work for us to do. All right, so first thing we notice from this equation here is that there is a consistent factor of 60x squared in every term. So let's factor that out. So 60x squared is multiplied by quantity x squared minus 3x plus 4, or plus 2, excuse me. So equals 0. First thing we can do is we can divide both sides by 60. And so if we do divide this left-hand side by 60, that cancels out this. If we divide the right-hand side by 60, we have 0 divided by 60, which is just 0. Okay. So we just effectively just cancel out that factor of 60. Next thing I'm going to do here is I'm going to take this quantity here and then factor it using the quadratic formula. Or if you can kind of just do this in your head, that works too. Okay. And so if we factor this, we see that it's a product of x minus 2 times x minus 1. Okay. Quadratic formula. Or you can factor however, whatever way you feel most comfortable with. We still have that value of x squared up there too. Now, at this point, you might be wondering, why, when we divided this entire equation by 60, why didn't we divide by x squared as well, right? So that's a common factor. Well, we're accounting for the factor where, we're kind of hedging our bets here in case that x does equal 0. Can we just leave a note here? Since at this point, x is to be determined, we don't know, we're kind of solving for it. We can't divide by x because x may be 0. In fact, x is equal to 0 is actually one of the extremes in this case. Okay. All right, so now that we have the derivative in this form, we can solve for all the values of x that make this 0. And so we're going to take each kind of term there individually and set it equal to 0. And so our three solutions are going to be x is equal to 0, x is equal to 2, and x is equal to 1. So those are all the values of x that make that derivative equal to 0. So you can plug in any one of those into that expression and you'll get 0. And so of course, these of course are going to be all of our extremes. So those are the values of x that we're going to be focusing on for the rest of the problem. All right, any questions on how we obtain those values there? Okay, question, yes.
Isn't it a little too early to say they're the extrema because we could have a saddle point?
That's true. That is a good point. So these are I would probably more accurate statement. These are where the slope of the functions equal. Yeah, that's good. Maybe another way we can say these are possible extremes. Okay, so let's go ahead and move on to the next step. So the next step here would be to classify each of these points. Okay. So to do that, we're going to take another derivative. We're going to have d squared f dx squared. Okay. And so we take that derivative. Then what we have for that is, I'm going to go from this form right here. And so the derivative of that first term will be 240x cubed. Derivative of the next term, which is 180x cubed, that's going to be minus 540x squared. And the derivative of that last term, 120x squared, would be 120x, or 240x. Right. And so our next step is to take this and evaluate the second order derivative at each of our possible extremes. Let's evaluate it first. Let's evaluate it first at x is equal to 1. And so if we evaluate this at x is equal to 1, I'm just going to plug in 1 into this expression here. So d squared f dx squared evaluated at x is equal to 1 is equal to 240 times 1 cubed minus 540 times 1 squared plus 240 times 1. Okay. We're just plugging in x is equal to 1 into our second order derivative there. And so if you process this, you get 240 plus 240 minus 540. And so what you get from that is a minus 60. So that's good. We get a non-zero number. That means we don't have to keep taking derivatives. Okay. And since this is a negative number, this tells us that x is equal to 1 is a maximum. All right, so that's good. Let's move on. So let's do the next part. So let's evaluate this at x is equal to 2. We take d squared f dx squared, evaluate x equal to 2. Okay. We have 240, 2 cubed, minus 540, 2 squared, plus 240 times 2. Okay. This one you probably need a calculator for. It's you know, a little bit more advanced. Okay. Right, luckily for me, I did this in the calculator over a year ago, so I already know the answer. So you plug all this in, and you get a positive 240, which is a positive number. Since this is a positive number, and since our derivative order in this case is even, it's the second order derivative, this tells us that x is equal to 2 is a minimum. All right, and then our final possible extrema was x is equal to 0, so let's go ahead and plug that in. We have e squared f, x squared, evaluated at equal to 0. Okay. So we have 240, 0 cubed, minus 540, 0 squared, plus 240 times 0. Okay. So we have 0 multiplied by everything, and so this gives us 0. And so this tells us that, you know, we can't draw a conclusion just yet. So we need to take one more derivative. We're going to take d cubed f, the x cubed. And so if we do that, we get 720 x squared plus or minus 1080 x plus 240. Just applying the power rule one more time. Let's plug in x equal to 0 into this expression here. So we plug in x equal to 0, we get 720, 0 squared, minus 1080 times 0, plus 240. Okay. We have the first two terms canceled out because they're multiplied by 0. And so what we get is 240, positive number. Okay. So, you know, when you're doing the classical methods, you know, you're basically just going to keep taking derivatives until you get a non-zero number. So that's what happened here. And so we have a non-zero number, positive. Okay. So normally when you get a positive number for this, that usually tells you you're at a minima. But remember that in order to get this positive number, we had to move on to the third derivative. And so since our derivative order here is odd, this tells us that x is equal to 0 is neither a max nor a min, it is a saddle point. Any questions on this example here? Okay. All right, so that's kind of the method, and so we've kind of tried it out in kind of two relatively simple cases. I have one more example for you today. We may not finish it just because the math is a little bit intense, but this last example here is a little bit closer to engineering. Okay. Okay, so let's actually work with an actual engineering system. So no more kind of just generic functions. So let's look at a two-stage compressor. Okay, so two-stage compressor, basically the whole idea of a compressor is to compress fluid. So you're basically going to run a fluid through the compressor, and it's either going to increase increase the pressure or make it go faster, right? So we have basically a system that looks like this. We have fluid coming in. Right, the fluid is going to come in, it's going to be compressed to a certain pressure P1. That's the first stage. Okay. In between the first stage and the second stage, there's going to be a cooling chamber. It's the cooling chamber. And so the reason there's a cooling chamber here is that it's been discovered that if you cool the fluid in between stage 1 and stage 2, it leads to a much more efficient process, and so you're kind of burning a lot less energy doing so. Okay, so the fluid's going to come into the first stage of the compressor P1. It's going to exit. It's going to go into the cooling chamber where it's going to be cooled at a certain pressure P2. The fluid is then going to leave that cooling chamber and then enter the second compressor. Where the second compressor is going to compress the fluid down to a pressure, or up to a pressure, P3. And the fluid's going to exit. Okay. This is first compressor. Second compressor. Cooling chamber in the all right. So anytime you have a thermal fluid process like this, usually, and you want to optimize the system, usually the thing that you want to optimize is total work or total energy input. Okay, so you want your processes to be as energy efficient as possible. And so what we want to minimize the total amount of work or total amount of energy needed for this process. And so that lends itself perfectly to an optimization. So if we can come up with a formula that kind of quantifies the amount of work or the amount of energy needed in this process, then we can work on minimizing it across our design variables. Okay. And so in fact, we do have such a function. And so we'll call that function W. And so that function W here is going to be the total work required for this process. Okay. This is going to be given by Cp times T1. Okay. I'll define all these variables in a second. Multiplied by the ratio of P2 over P1 raised to the power of K minus 1 divided by K plus the ratio of P3 over P2 raised to the power of K minus 1 divided by K, excuse me, minus 2. Okay, so let's define these variables. So CP here is the specific heat of the gas or the fluid. T1, that is the inlet temperature of the gas, and so that's the temperature that the gas starts at. K. K is the ratio of the specific heats at constant pressure to the specific heat at constant volume. So it's a common thermodynamic quantity that's often tabulated for gas. We'll call it the ratio of specific heats, and so this is the ratio of constant pressure constant volume and of course P2, P1, P2, P3, those are the pressures at each stage of this process. Okay. Of course, the last variable there is 2, but 2 is just 2. All right. So we have a much more complicated objective function in this case, and so we have a function here at W. That's going to be our objective function because that's what we want to minimize. Okay. But of course, we only have methods for 1D optimization, so we can't run this. We can't consider everything as a variable here. And so for this particular problem, we're going to optimize over the cooling pressure P2. You want to find the optimal cooling pressure P2 that minimizes the work. So that's our one design variable. Everything else in the problem here, P1, P3, K, CP, P1, everything else is just going to be a constant. In other words, what we often say is all other variables are fixed. And if they're fixed, we can basically, we don't have to consider them in the optimization. All right, any questions on just the setup of the problem, or hopefully everything makes sense in the vector function here? Okay. All right, so let's get to optimizing this. And so even though we have a much more complicated equation here, we have a lot of symbols here. The majority of them are just going to be constant. So we can just follow the same procedure as before. And so the first step in our classical optimization procedure is to simply take the derivative. gonna take the derivative of our work function. And since P2 is our design variable of interest, we're gonna take the derivative of W with respect to P2. All right, so since this one's a bit more complicated, you know, I'll go a little bit more step by step, okay? In other words, we're gonna take dP2 of the quantity CPT1 multiplied by P2 1 raised to the power of K minus 1 K plus P3 over P2 K minus 1 K all minus 2. But I didn't do any derivatives yet. All I did was just kind of write the function. All right. It looks daunting, but you know, we're going to take advantage of some, you know, properties of derivatives in order to kind of make this easier. All right, so first thing we're going to do is we're going to take advantage of the fact that derivatives are a linear operator, and so that means we can distribute it to each individual term. Okay. And then just any constants are just going to factor out. So first of all, first thing we notice is that CPT1, that is just, those are both just constants that are multiplying this entire thing. So we can factor that out of the derivative completely. We have CPT1. We're effectively going to just forget about it for now. Then we're going to take the derivative of quantity P over P2 over P1 raised to the K minus 1 over K. Plus derivative of P2 of quantity P3 over P2 raised to the K minus 1 over K minus dP2 of 2. Okay. And of course, that last term there is just going to go to 0 because you know, it's just a constant. Okay. So we have two derivatives to take care of here. So we have the derivative of the first term and derivative of the second term. Okay. Let's make our lives a little bit easier in this case because we know that P1 and P3 are just constants. And so let's factor those out of the derivative. So I'm just going to pull those out just to kind of make our derivative as clean as possible. Okay. Next thing I'm going to do, another thing I'm going to do in this step just to make sure we get to this part. I don't think we'll finish the full example today, but I at least want to give you the value. Okay. We'll do the checking next time. I'm going to simplify that exponent. This formula is kind of something straight out of a thermodynamics textbook, so it's kind of designed just to kind of look pretty. But you know, when you're taking derivatives and you're doing optimization, it's kind of useful to have things in another form. Okay. So our exponent for both of those terms is K minus 1 over K. Okay. And so if we distribute that 1 over K to each of those terms, we get 1 minus 1 over K. Okay. Seems like a very simple thing, but you know, you're going to see soon that when we take derivatives and we take the power rule, this form is going to actually be quite useful. Okay, so let's go ahead and do both of those things at the same time. So we still have CP T1 multiply by quantity. I'm gonna factor out that 1 over P1 term. We have 1 over P1 raised to the power of 1 plus 1 k times the derivative d2 of P2 raised to the power of 1 minus 1 over k. Okay. Plus we have P3. We factor that out of the derivative. We're going to raise that to the power of 1 minus 1 over k. And we have derivative of with respect to dp2, 1 over p2 quantity raised to 1 minus 1 over k. All right, so this is nice here, right? So the first term we can probably deal with this, right? Because if we take the derivative of this first term and we kind of treat it just like a polynomial, right? And so if we take the derivative, usually when we take the derivative, we subtract 1 from the exponent, we bring that number out in front, and then we're kind of left with this. So this quantity here is actually easy to evaluate. So this quantity here is P2 raised to the minus 1 over k. So you can see that's why we put it in that form. So we have that 1 that's kind of floating out in front. And so we take the derivative, we just kill that 1, and we just kind of are left with whatever's left. Okay. This term here also fairly straightforward, but it may be a little bit easier to put it in a more convenient. Okay. So first thing we notice here is that we have 1 over P2 in there, right? We know that if we take the reciprocal of a variable, one way that we can do that is we can turn its exponent negative. Okay. Let's take the reciprocal. We have P2, P2. So I'm going to bring that P2 into the numerator, and then by in order to do this, we have to change its exponents to negative, right? And so we have a minus 2 plus 1 over. Or excuse me, minus 1. Jumped ahead of myself. I took the derivative. So all I did was I took the reciprocal and then I just multiplied the exponent by a minus 1. So that gives us minus 1 plus 1 over. Okay. Now that we have it in this form, now that the P1 is up top, we can take the derivative in exactly the same way. And so we're going to take the exponent, subtract it by 1, and then bring that factor out. And so if we subtract by so we subtract 1 here, we get P2 times raised to the power of minus 2 plus 1 over k. Or excuse me, minus 1, sorry. Sure. Well, it is minus 2. Tripping all over myself. I'm getting excited because next class we're doing again, so I'll find it element class. Excited. Okay. Of course, I did forget one thing here. So whenever we do the power rule, we have to multiply that factor out in front, right? And so for this first one here, we have to multiply this by a factor of k, or excuse me, 1 minus 1 over k. And for this one here, we're going to multiply by a factor of minus 1 plus 1. So these right here, these are the power rule exponents. Okay. So now that we've taken the derivative, every term is accounted for now, and so let me go ahead and write out the final expression. So dw dp2 equal to cp t1 multiplied by quantity 1 over p1 raised to the power of k minus 1 k multiplied by factor of 1 minus 1 over k 2 raised to minus 1 over k plus p3 raised to the power of k minus 1 k multiplied by factor minus 1 plus 1 over k times p2 raised to the minus 2 plus 1 over k. Now we can set that entire thing equal to 0. Okay. And so, if we had more time, then we can take this expression and solve it for P2. But since we're out of time, I'll go ahead and give it to you. And so the answer is actually quite elegant. Okay. And so the value of P2 that minimizes this, or that is an extreme, and we'll find out if it's a minimum next time. Although I kind of just spoiled the insertion. Okay. And so nice thing about this is we get just one solution for P2. That's the product of P1 times P3 raised to the 1/2 power. So that is the one possible extreme for this function. So when we come back on Tuesday, we'll finish up this example. We'll take the second derivative and find out whether this is a max, a min, or neither. Okay. All right. So thank you guys for coming this week. I apologize for going. I think I went over a little bit on Tuesday too. I try not to make it habit of this, but I appreciate you guys sticking around. Hope you guys have a good weekend. Stay cool. I don't want no one should be getting heat stroke over the weekend. Please, stay in air conditioning, stay hydrated, and I will see you guys on Tuesday.
I'll be on to it.
Hey, Professor, I just had a quick question.
What? Or?
My code.
Oh.
I still work because I can't even do it. I can't do this.
How do you do that?
auditory thing.
Yeah, sorry, I had a quick question. So I was on the wait list and I just got the permit to re-enroll, so I dropped the class and re-enrolled. As far as the Canvas goes, I'm still not able to see anything, so is there something I need to?
I think probably you should get access to the Canvas probably end of today. I think some of those two are separate systems. But if you're still not getting access by tomorrow.
I haven't
just send me
taken
an email,
10 yet. So
and I
it's
can
an
add it to
entry.
Canvas.
Okay, for sure, sounds good. All right, thank you, Professor.
No, I said I haven't taken it yet. So like
No one's gonna believe me
Yeah.
when I report you, huh?
Did
in
you
high
get
school,
the?
we had this thing called the
I
bully
think they
box.
sent out the
We'd always say
permits.
like, I'm gonna report you to the bully
Yeah,
box.
yeah, so if you got one, then just go ahead and use it.
Yeah,
But
my
if not, then
house,
that's
like,
that's pretty
I
much
got
it.
these like
You're tired?
Celsius packets.
Would you, do you have a mouse that you're using?
So
Honestly,
I
don't know.
allowed,
It's randomly, like, at start,
top
I'm
five,
always,
but
I'm just like.
top 5 on the wait list plus a couple kind of special.
And I just like said like, oh wait, I got candy. So I popped a candy. I was like, oh,
Yeah, unfortunately not, so
No,
didn't get a
like,
permit.
That was so
you have
funny.
to for-
How like. So there's like what's in here? There's trolley and pickle patches.
and yeah, I run.
Oh, yeah.
I think they're trying to send a message
I
to.
know.
For this class, unfortunately not.
I
This-
think
that-
mine
this
kind of has that. Because I started because I didn't get one actually. Just to
Yeah.
somebody didn't want theirs at the school. I had it because it's the table. So I was like, okay, I'll get the trolley
Yeah.
and the cup because yeah, and the cup because
Oh,
I
yeah, yeah.
need cups.
I have a bunch of
So
cups.
good. Down in the lake class and then.
Dude, I don't understand.
Okay, I'll go out.
Yeah, no, I got. Yeah.
Thank you.
How do you copy and-
I was.
What? Oh, yeah, I bought it. It took forever though.
I saw it.
I'm looking-
I think you have to re-file it and then try adding.
I gotta go.
Yeah.
See you guys later.
The system's a really weird this year.
I'm gonna go to office hours for my math class. So, are you guys heading out right now?
Yeah.
Are you gonna stay?
I'm gonna.
That's good, that's good, that's good.
I'm looking forward to it.
Yeah.
It's fun stuff.
Yeah, no, it's a cool, I really like the class.
I think we can talk about. Dude, when you over there,
A lot of, what up?
We want to like, look at and then we'll do like.
Oh, yeah. Oh, yeah, yeah.
Smooth way level.
Yeah, so that's right. So what you're describing is a multi-stage optimization. So,
Okay.
yeah, that's a very common technique, but then, you know, the science of like choosing which variables to group, it's so system specific. And so, you know, even for systems that people feel like they have a good grasp on, there's still so many different combinations of like algorithms that you can use and different stuff, even for different stages, use different algorithms. So, yeah. Optimization is really
That's such a smart thing. You can throw in like 10, but you might not live this.
Yeah. 10 is actually not bad. You can do 10, but there's some optimization that go like.
Okay, was it targeted?
Yeah.
Okay.
Yeah. It's great. I hope you like the.
I'm very excited, so I will see you next week.
I didn't spend that much in a month.
Did you buy a laptop?
I didn't.